Good afternoon. I have the pleasure to be your host today and present to you all Professor Michael Hore. He is an associate professor at the Department of Macromolecular Science and Engineering of Case Western Reserve University. He earned his PhD in Material Science and Engineering from the University of Pennsylvania. He received a National Research Council postdoctoral fellowship to perform neutron scattering measurement at the NIST Center for Neutron Research, studying nanoparticles in solution, as well as polymer phase behavior and structure using small-angle neutron scattering and neutron reflectometry. He has been recognized with several teaching awards, an NSF Career Award, and was named a 2018 PMSE Young Investigator by the American Chemical Society. Inside his line of research, he combines experiment theory and simulation to study fundamental problems in polymer physics and grafted and non-linear polymers. So welcome, Professor. Thank you so much for being here, and feel free to start your presentation.
Thank you very much. Let me share my screen here. Hope that's coming through okay.
Yes.
Okay, great. So what I thought I'd talk about today is some recent work that we've done, and by recent, I mean less than a year old. And it's combining this Flory-Rehner theory of polymer microgels with the Daoud-Cotton model that we use to describe polymer nanoparticles. But first, I thought I'd talk about what we do in my group. And so you can see that we have four main areas that we work in. We work in grafted polymers, and we look at the structure and dynamics. We work in responsive polymers, nanoparticle transport, and also scattering methods. To give you kind of a flavor of what that means, in terms of responsive polymers, we're interested in things like polynipam and related polymers. And just as a quick example, one thing that we noticed when we synthesized these is that this end group here on the polymer, the number of carbons determined what it did in solution. So if it had, for example, 12 carbons on the end of the polymer, we noticed that it self-assembled into micelles, whereas with the shorter end group here, the ethyl group, it just existed as free polymers in solution. So certainly people had seen this before, but we were the first people to really look at this with neutron scattering. And what we found is that the transition temperature, where the polymer goes from a coil to a globule, really depended on how the polymer was assembled. So we matched up our neutron scattering measurements that we analyzed quantitatively with DPD simulations to see if we would get something reasonable and could understand it. We also look at nanoparticle transport. So we look at the transport of nanoparticles through single confining nanochannels. So I've shown it schematically here, but here's a TEM image of what the nanochannel actually looks like. And these have diameters anywhere from 40 to 100 nanometers and lengths of about 100 nanometers. And what we record is the ionic current through the channel as a function of time, and we get these characteristic resistive pulses due to the blockage of the current through the pore. And then our goal after that is to analyze these pulses to understand what's going on in terms of the transport of the nanoparticles. We do a lot of scattering, and so here are two PhD students who went to the NIST Center for Neutron Research to do scattering measurements, and I'm going to talk quite a bit about scattering today. But when we analyze our scattering data, a lot of times it requires that we develop new models. And I'm showing one example here for a protein that's grafted with a polymer chain. So we spend some time developing these models and testing these models, and then we release them as open source software to the community for use with, for example, the SASView software package. Today, however, I'm just going to focus on the grafted polymers and especially the structure and dynamics of polymer chains that are grafted to spherical nanoparticles. So you may well be aware of why we might do this. And so the first example that stands out is the formation of polymer nanocomposites, where we can combine the physical properties of the nanoparticles with the physical properties of a polymer matrix. And over 10 years ago now, these investigators noticed that when they had nanoparticles, these were silica that were grafted with polystyrene. When they put them inside of a polystyrene film, they got different structures depending on the molecular weights of the polymers that were involved. So this was interesting just from a pure polymer physics standpoint, but it also has real implications in terms of the mechanical properties of the material. So you can see here that the morphology, whether it's strings, kind of like up here, dispersed or fractal-like structures, jammed states, these significant fracture strain of the material. So we can move beyond spherical particles and we can look at other things that are maybe more responsive, such as gold nanoparticles. And so I'm showing you an example here where this is a polymer, not really a film, but a thin strip of polymer that has a small amount of gold nanoparticles in it, and it's initially created in this kind of spiral shape here. Now, the equilibrium shape that the material wants to have is this elongated state. And so by shining a laser at the appropriate wavelength onto the nanocomposite, the gold nanoparticles cause it to heat, and that heat can trigger the shape memory transition. We can also use these to create long strings of nanoparticles that can act as polarizers and further impart some kind of optical response to our materials. So the point that I'm trying to make here is that dispersion of nanoparticles and the morphology of that dispersion within a material is of great importance for the physical properties. We can even go one step further, and we can look at something like NIPAM that we've studied in solution. And this polymer is quite interesting because the monomer has this hydrophilic region as well as this hydrophobic region. And as I showed earlier, you can tune the end groups of the polymer chain. And those properties are going to impact its thermal responsiveness. So what's observed is that as you heat poly-NIPAM up above 30 degrees, the chains move from this coiled-like state, which is expected of a polymer in solution, to a globule state. So you see, you can trigger this actuation of the polymer chain, and presumably the origin of that effect is that the strength of the interactions between this monomer here and the solvent are changing as temperature increases. So this has LCST behavior in water. And this is an example from a couple of years ago showing how this can be used to trigger folding of poly-NIPAM gels in response to heating by a laser. So that's kind of an overview of the kinds of things that these particles that I'm going to talk about today are useful for. And so now I want to talk a little bit more about the underlying polymer physics that's really going on here. So one of the easiest ways to disperse these nanoparticles within a material is to graft a polymer to the surface. I think this is well appreciated by now. And because most polymers are immiscible, one of the most simple ways to do this is to make sure that the chemical composition of the grafted chain and the free polymers are the same. So for example, a polystyrene brush inside of a polystyrene matrix. And what's known is that as you increase the molecular weight of the matrix polymer, while keeping that of the brush the same, you're going to get stretching penalties if you want the red matrix chains to wet the brush. So what's going to happen is these stretching penalties are going to end up causing depletion attractions between the nanoparticles, and that's why you saw those different morphologies of the silica particles in the polystyrene matrix. From my own work, this is true for gold nanorods too. In this case, these gold nanorods are the same nanorods. They came from the same batch that was synthesized, and all that's been changed here is the molecular weight of the matrix, and you can see that the morphology is quite different of the nanoparticles. And so it's simply this autophobic de-wetting, so this process here that's entropic in nature that gives rise to the myriad structures that we see for nanoparticles in these materials. And by now we've mapped out phase maps for spherical particles and rod-like particles. So we have a pretty good understanding of the physics behind this. What was puzzling though, is you can perform self-consistent field theory calculations to calculate the density of the brush away from the nanoparticle surface and correspondingly the density of the matrix. And although you see these huge effects in terms of the dispersion of the nanoparticles, what you don't really see is an appreciable difference in the density of the brush. But at the same time, if you look at the diffusion of polymers inside of a polymer matrix, so this kind of mutual diffusion problem, you can cast the diffusion coefficients of a polymer in a nanocomposite onto this master curve. And really all it depends on here is the size of the nanoparticles. But from the same self-consistent field theory calculations, we see that this autophobic effect changes the effective size of the nanoparticles. So clearly something is going on here, and that's what kind of motivated this project to understand these phenomena. So what I'm going to talk about first today is the conformation of a polymer that's grafted to a nanoparticle surface. And so I think all of you have a polymer background, but in case you don't, if I have a polymer chain that's made up of this many monomers or beads, one of the things that I'd like to talk about is how big that polymer chain is. And the easiest way to do that is to talk about its radius of gyration, which is effectively the average distance that these monomers are from the center of mass of the molecule. And you can see that it scales as the number of beads to the 2 times nu power. So that nu is the Flory exponent, and it tells us about the shape of a chain, whether it's an ideal Gaussian chain, whether it's swollen or whether it's collapsed. So for example, when polynipam collapses of its LCST. The next thing that I want to talk about is the dynamics of the polymer chains when they're grafted to nanoparticles. That's going to affect the mechanical properties that you can maybe see in this graph on the right here, where the storage and loss modulus of these composites was measured as a function of the grafting density of the polymer chains. And you see you get different responses, whether the chains are untethered or not grafted to the particle, at a high density or at a relatively low density. Corresponding to that, these researchers measured the relaxation times of the chains. And if you just focus on these diamonds here and these diamonds here, the black diamonds are the tethered chains. The open diamonds are the untethered chains. And you see that the relaxation time of the tethered chains is much longer than that of the untethered chains. But as you increase the molecular weight, these differences start to disappear and the 2 sets of lines start to approach each other. So one last kind of introduction here is that when I talk about the relaxation dynamics of the polymer chain, it's helpful to think back to what happens to a bead in solution, where if it's moving at a constant drift velocity, it's going to experience a drag force. So from the Stokes-Einstein relationship, we can understand what the diffusion coefficient is in this case. And more importantly, for the talk today, we can define a characteristic timescale for the relaxation. This timescale here is nothing more than the time it takes a particle to diffuse a distance that's equal to its size. So like this. Now, if I have a polymer chain of many beads, I can modify this theory. And the important thing to note here is that there are many different length scales. And so what I get is a spectrum of relaxation times. And it's those spectra, or that spectrum, that I want to measure. So in today's talk, what I want to really discuss is what is the structure of a polymer that's grafted to a spherical nanoparticle? What impact does this structure have on the relaxation dynamics of the polymers that are grafted? And how can we take into account the behavior of thermoresponsive brushes, such as in the case of NIPAM? So let's talk about the first 2 first. This is work that's about 2 years old. And the starting point for this is what we know theoretically from the past about what the structure should be. And so the starting point for describing the structure is that of the star polymer. And so in 1982, Daoud and Cotton derived a model for how the conformation of an arm of a star polymer should change as a function of distance from the core, as well as a function of the number of arms that are on the particle. Later on, this model was extended to include a large core for the molecule, which is exactly the case that you have when you have a polymer grafted nanoparticle. So you can see in this schematic from the original paper in 1982 that you can represent the core in a way that looks like a nanoparticle, and you can see that the polymer is stretched locally and becomes more relaxed as you move farther away. Now, specifically what that means for a nanoparticle is that if you have a low grafting density, you're just going to have an ideal chain that kind of is tethered to the surface of the nanoparticle. But as you increase the grafting density, you get 2 regions. You have a concentrated polymer brush close to the core, and after a cutoff distance RC here, it transitions to a semi-dilute polymer brush. So what I want to emphasize here is that these 2 regions are differences in concentration, but there are not necessarily differences in conformation. But the cutoff distance between these two regions, using the Daoud-Cotton model, can be expressed as the product of the radius of the nanoparticle, the square root of a reduced grafting density of polymers, and this term in the denominator, the excluded volume, that I'm going to talk about in the last part of the talk today. So people have done this before, and one of the easiest ways to identify this behavior is not to do neutron scattering, but to prepare many different molecular weights of polymer grafted nanoparticles and just measure what their hydrodynamic radius is or what their hydrodynamic diameter is. And you will observe that the diameter of the particle scales as n to the 0.8 power up until some cutoff distance and then transition to n to the 0.5 power. So out in this region, in the semi-dilute region, the polymer chains are more ideal. But closer to the polymer core, this 0.8 power here is implying that the chains are more stretched close to the core. Other people have also done it by looking at TEM images and kind of measuring the thickness of the brush that they can observe. So we take a different approach to this, and we use neutron scattering. So if you've never seen these instruments, this is at the NIST Center for Neutron Research outside of Washington, DC. And there's a nuclear reactor back here that's 20 megawatts, using high enriched uranium to enhance the number of neutrons that come out. This instrument here is 30 meters long, and it's the small angle neutron scattering instrument for structure, painted this nice bright purple. This instrument here is the neutron spin echo instrument, which is analogous to NMR, but using neutrons instead. You can see by the ladder here and by the size of this pump here, these are gigantic instruments. And so this instrument, the spin echo instrument, will measure the dynamics or the relaxation times of polymers from about 3 picoseconds to 300 nanoseconds. It has the largest time range of any neutron spectrometer. So why would we do this when we can just do DLS? I'll show you an example. Here's this example here, just this particle here is a virus-like particle. So it's a self-assembled protein capsid. And we grafted polymer chains to it. And you can actually do cryo-electron microscopy and resolve the structure of the core and the structure of the grafted polymers here. We got lucky in this case that we could do that, but in general, you can't. So what happened in terms of the actual experiment is we did the neutron scattering first, and we saw this very odd-shaped curve, which says to a scatterer, oh, you must have this raspberry-like structure. Then we went back and looked at the structure of these particles. But you can't always do that. You don't always have the contrast in the electron microscope to see this. So if you think about the earlier image I showed you where researchers are using TEM to look at the brush thickness, the point I'm trying to make here is that you're missing a lot of potential detail in what the particles have. Another advantage to neutron scattering is that whereas X-rays don't really respond or scatter much from light elements, neutrons do. And neutrons are sensitive to the isotopes, so deuterium and hydrogen scatter quite differently from each other. So we can get contrast that way. And just by eye, you can see the differences between an image taken with X-rays and an image taken with neutron in terms of what absorbs and what doesn't absorb. So we can perform these measurements and we get curves that look like this. And so these are typical curves for polymer grafted nanoparticles. And all I want to do here is return back to the original question, which was the self-consistent field theory showed that there was no appreciable difference in the density of the brush. This Daoud-Cotton model predicted that the cutoff distance between this concentrated region and the semi-dilute region was around 5.6 to 7 nanometers. And when we did the neutron scattering and fit with our model, which I'm showing in red here, we were able to not only get a good fit, but confirm that, first of all, according to New here, this is the Flory exponent, the chains were roughly Gaussian. In blue here, this value of RC 6.5 nanometers is exactly within the range of the Daoud-Cotton model. And the RG of the polymer in the semi-dilute region didn't change much. So this kind of like brings everything together and kind of unifies our picture of these polymer grafted nanoparticles directly. But the question is, can we do better than this? And this is the more recent study, because what we'd like to do, that previous example was iron oxide nanoparticles, which are bad for spin echo. Spin echo uses very, very strong magnets, so we can't have particles that can have a magnetic moment. What I just showed you, we never actually measured the conformation of the chains in the stretched region. We assumed it was a uniform density shell of polymer. So can we address that? So what we did instead was use silica that's 12 nanometers in diameter from Nissan. We can predict that RC for this particular system is about 15 nanometers. We used a different polymer. The previous example was polymethyl methacrylate. We're going to use polymethyl acrylate instead because its glass transition temperature is 10 degrees. And if we want to measure the dynamics, we'd like to get well above the glass transition temperature. We synthesize these polymers ourselves. And the system that we chose has natural contrast matching between silica, the solvent that we use, which is tetrachloroethane, and the methyl acrylate monomer when it's partially deuterated. And I'll speak a little bit about what I mean by contrast match in a second. But the objective here is that for one set of samples, we can hydrogenate the concentrated region and deuterate the semi-dilute region, and then switch that deuteration scheme for the second set of samples. So in one, we will highlight the scattering from the concentrated region and hide the scattering out here. And in the other sample, we'll reverse what we're seeing with the neutrons. So what I mean by that is if you look at these nanoparticles here, the red is the core of the particle, and the yellow is the polymer brush, and the blue is the solvent. So by mixing together different ratios of deuterated and hydrogenated solvent, we can, for example, hide the core and only scatter from the brush. Or if we contrast match the shell by using a different mixture of hydrogenated and deuterated solvent, we could only scatter from the core. So this is a huge advantage for neutron scattering. And I also put this in there, this is a huge advantage for polymer synthesis, because these polymers that we needed are not available commercially. So we had to find these ourselves. Synthesize these ourselves. So this is the system that we ended up looking at. To measure the structure of the concentrated polymer brush region, we had a hydrogenated block that was close to the nanoparticle surface. It was followed with a deuterated block farther away. So the molecular weight of the inner region was about 17 kilograms per mole with a low dispersity. And then farther out, we had a smaller molecular weight. We had 6 kilograms per mole. The dispersity of the entire polymer was relatively high, but it's okay. It's within the range that's acceptable for neutron scattering measurements. Now, one thing that people ask me, especially when they see the next sample, is why is this molecular weight so low? Well, it turns out that, first of all, this monomer is very expensive. It's about $3,000 US per gram. So we didn't want to use too much of it. Also, there's no scattering from this region out here. So we're not getting anything out of it. With the reverse case, we're going to measure the opposite, but in this case, we wanted to match the molecular weight of the inner region to that of the previous sample. And then since we are scattering from the polymer chain out here, we did increase its molar mass. And you can see the characteristics of the polymers are quite similar. So when I mentioned the research areas that my group works in, one of the things I mentioned is we like to develop new models, or sometimes we have to develop new models in order to be able to interpret the scattering. And so I'm showing schematically here how we analyze the scattering from such a complicated sample. And the scattering consists of terms that are just scattering from atoms in the core, just from scattering in the grafted chains themselves. And then there are cross terms between the core and the different blocks of the polymer. So the core in the inner region, the core in the outer region. And then you also have corresponding correlation terms between the polymer chains themselves. So you end up with a function that has these 7 terms. But what I want to emphasize is there's maybe 2 at most free parameters that we're fitting here. So it's a really well-defined model, and then we analyze our scattering this way. So here's our data, and you can see that although these samples are very similar, the scattering from them is actually quite distinct here. So this polymer chain here, or sorry, this sample here has the hydrogenated inner block, and then the deuterated outer block. This sample in blue here has the opposite deuteration scheme. And hopefully what you can notice is that the model that I just described to you in red fits the data quite well. And again, we can narrow down the parameters that we use here. So the diameter of the core is fixed because we know that. We know the grafting density, so we know how many polymers there are. We know the molar masses of the polymers and the different blocks of the polymers. We know the Kuhn length and things like that. So really, the only thing that we're fitting here is the value of RC when the brush transitions from a concentrated to a semi-dilute region. The sizes, the radius of gyration of both blocks, and then the Flory exponent of both blocks. So what we found here for the sample that had the hydrogenated CPB is what I'm showing schematically here. And the reason that I chose these colors that are hard to discern is because this is what the neutrons are seeing when they scatter from the particle. The scattering length of the silica core and the solvent are almost the same. So there's very low contrast between these two. Similarly, the contrast between the deuterated outer block and the solvent is very low, and it's almost the same as silica. So these don't have a lot of scattering length density difference, whereas the hydrogenated chain does. So we were able to see very clearly that the radius of gyration of this inner region here was about 10 nanometers. It's really small here, but the scaling exponent was about 0.8, which is indicating that the chain in the inner region is actually highly stretched like we anticipated. And the cutoff distance between the concentrated and the semi-dilute polymer brush regions was about 20 nanometers, 18 nanometers. Just based on our rough estimate, we figured that this was about 15 nanometers. So our estimate was off by 3 nanometers or so. So not too bad. Finally, we were able to see a little bit of the polymer chain out here, but the scattering was very weak, but it had a smaller size of 3.2 nanometers. And if you remember, the molecular weight of that outer block was actually quite small. It was 6 kilograms per mole. So now if we look at the different sample, the reverse deuteration scheme, things got very tricky because the contrast between the silica core and the stretched polymer brush, the concentrated polymer brush region, was really washed out and blurred due to the low contrast between the two. So we saw this blurry core here, and then the core was decorated with polymer chains that had a radius of gyration that was a little larger than the previous case, of 4 nanometers. And what I want to emphasize here is that the outer region in both cases showed a scaling exponent of 0.6. So if we step back and think about what that means, it means that the polymer chains on the outer region of the particle were just swollen chains, as you'd expect for a polymer in a good solvent. So we really did separately look at the structure of these different regions, and they were in good agreement with what we expected from theoretical arguments. So spin echo is able to probe the relaxation times of the polymer chains at different length scales and at different times. So in terms of the length scales, or the Q space that it's sensitive to, we're looking out here at these regions of the scattering graphs. So again, this is what spin echo data looks like. This is the normalized intermediate scattering function. But if you know nothing about intermediate scattering functions, and if you know nothing about spin echo, what you can see by looking at this graph already is that these open points here, which are which describes the relaxation of the stretched region, are quite distinct from the filled points here, which describes the relaxation of the outer region. And what I'll tell you is that if there was no relaxation, if we were not observing any relaxation, then this function would just be 1. So we can already see that there is a difference in the relaxation times of the inner and the outer regions of the brush. So we have to fit this somehow. Since we're looking at solvent, one model that we can use for the dynamics is the Zim model, which incorporates hydrodynamic effects. So if you're familiar with this model, this may look a little different than how it's typically presented, but this is how it appears in terms of the intermediate scattering function. And basically, the intermediate scattering function here will decay as this stretched exponential with this exponent here of 0.85. And then this term here takes into account the fact that the nanoparticles are diffusing in solution at the same time. So this tau is the relaxation time we're going to fit for by fitting this function here. And we'll get the nanoparticle diffusion coefficient from DLS. So we can combine everything together here. So here's not all of the data, but a lot of the data. The data I showed on the previous slide is still shown in black here. And what we're doing is we're changing the value of Q. So we're going to different length scales. So each color is a different length scale in the brush. And what you can observe is that no matter which length scale we're looking at, the dashed line is always quite distinct from the solid line. That's true in the red and that's true in the blue. So we're looking at relaxation times over length scales of 11 nanometers here to relaxation times over length scales of 4.5 nanometers. So we're going from relatively big relaxation, or the relaxation times of relatively big regions, to the relaxation times of very local regions here. So we're going from large scales to smaller scales. So we can fit these data and we can tabulate what we observe, and we find that the relaxation times decay as Q to the minus 2.5, and all that's saying is that we get good agreement with the Zim model. But more importantly, you see that even at local length scales out here, the concentrated region, the region that's more stretched, is relaxing more slowly than the unconfined region farther away by a factor of about 3. It's also worth noting this is on the order of a couple of Kuhn segments here. So even very locally, this effect persists. Now, this is just a brief slide. I never published this. I will never publish this probably, but this was the iron oxide particles that we measured originally. And the work I showed you was in a polymer film. This is in solution in deuterated toluene. But by fitting these curves with the same model that I showed you before, we can get an idea of how much solvent is in the brush. And just a rough back of the envelope calculation shows that of the moles of everything that's in the brush, including the polymer and the solvent makes up about 88% of the atoms in the brush region. So it's to say that perhaps it's not surprising that we can apply the Zim model so nicely, even in the concentrated brush region where there's a large amount of monomers. So to summarize this first part of the talk, we did 2 things. We looked at the structure of grafted polymer chains, specifically on spherical nanoparticles. We developed a new model that I only showed you schematically, but it allowed us to directly probe the 2 different regions of the polymer brush. And we highlighted the scattering from each of those regions by selectively deuterating them. So as we expected from theories, the inner concentrated region had highly stretched chains that scaled as n to the 0.8 power, while farther away, the semi-dilute region, or the portion of the chain in the semi-dilute region, had more ideal conformations. Its conformation was that more similar to a swollen polymer chain than of a stretched polymer chain. To kind of make sense of the observations that have been made experimentally about the dynamics, we performed the first spin echo measurement of the local dynamics of a polymer brush. And this is a unique capability of neutron scattering that again results from us being able to selectively deuterate the 2 regions. The dynamics in the concentrated region were at least 3 times slower than that of the semi-dilute region. And so that explains why when you have shorter chains, you see such a huge difference between the grafted chains and the free chains, whereas when you start increasing the molecular weight of the brush, the 2 start behaving more similarly to each other. So the last little section of this talk is more recent work that we did within the last year. And the question is, how do we take into account the behavior of thermoresponsive brushes? And why would I ask that question in the first place? Well, it starts from the previous study. Tetrachloroethane is a fantastic solvent. And if you're not familiar with it, it's a very, very toxic solvent. So be careful with it if you use it. but it's a great solvent, and it's one of the best solvents around for PMA, which meant that at these different temperatures, we wouldn't necessarily expect such a huge change in the conformation of the brush, because it's such a great solvent that we wouldn't expect much change in the region of temperature that we could access. On the other hand, NIPAM and D2O, we know that it has LCST behavior, and we know that that critical temperature is around 32 degrees. So if we go back to the Daoud-Cotton model, the cutoff distance between these two regions, I filled in a little bit more of the details here, is a product of the diameter of the core, the grafting density, the Kuhn length, and the excluded volume. And this is exactly equal to the dimensionless second virial coefficient. So if we can get thermodynamic data, then we should be able to predict where this is, and we can test how well this model actually works for a responsive system. So we can go into the literature, and we can go back to 1990, and actually the second virial coefficient has been measured, and we just have to renormalize this to get the dimensionless version. But you can observe that there's quite a bit of variation here. This value of 0 is taken at the theta temperature, which is 30.5 degrees. These values are taken at 20 degrees C, and you see that they vary from each other. And the only thing that's changing here is the molecular weight of the polymer. So there's a molecular weight effect that's showing up in the virial coefficient. But we do see that as we cool down poly-NIPAM, the second virial coefficient is increasing, which shows us that the solvation is getting stronger as we go to lower temperatures. So this has the effect that we're hoping to test. But we can look further in the literature. And this is from 1995. And unfortunately, there aren't that many measurements outside of these three that I'm showing you. This is poly-NIPAM at 20 degrees C in water with a molecular weight that's actually similar. It's actually between the two values here in the previous study. Second virial coefficient is negative, which implies that the solvation is not so great. Well, if you look at the Daoud-Cotton model, if this goes negative, then what does that mean for RC? It becomes negative, which is kind of nonsensical. So there's two observations. One is that there's variation in the thermodynamic values of NIPAM at 20 degrees C. These could be concentration effects, molecular weight effects. It varies as a function of temperature. And also, I showed you three studies. That's about all we could find. So despite the lack of thermodynamic information for poly-NIPAM homopolymer, there are quite a few studies of DLS measurements of NIPAM microgels. So the question is, can we combine these two approaches to somehow resolve how we would calculate the transition point between these two regions? And I found a great quote in the abstract of a paper that I'd like to read to you that really highlights the problem here. The very first sentence says, major, still unelucidated inconsistencies exist in the literature among measurements of the thermodynamic properties of NIPAM solutions and gels. So potentially neutron scattering measurements can help resolve these inconsistencies, or at least give us some idea of maybe which values are closer to what the true values may be. So the Flory-Rehner theory is looking at a polymer gel or a polymer network that's put into a favorable solvent and then swells, I guess, to become a gel. And it results from setting the contributions to the osmotic pressure from the elastic component from all these chains to that of the polymer and solvent mixing together when it's placed into the solvent. So after some manipulation of the two expressions, you get the Flory-Huggins interaction parameter that you can express as 1/2 minus this coefficient here, times this quantity that depends on the theta temperature, the temperature of the solution, and then some higher order terms. And that's equal to some function that's, that contains the volume fraction of polymer and the dry volume fraction. So what the volume fraction is like without any solvent. And so the dimensionless second virial coefficient is 1/2 minus that. So we get this quantity here. So we're only left with the second term. And we can substitute that in for the second virial coefficient here, and we arrive at this expression. And these absolute value symbols were derived rigorously. So I didn't just put them. There's a process you can go through to get those. And so the point is this. this is what people measure for microgels. They do DLS to get the hydrodynamic radius of the gels as a function of temperature for different cross-linking densities. And they can extract the thermodynamic properties of the NIPAM water system that way. And our hypothesis was that we can use this thermodynamic information to predict the structure of NIPAM. And then we arrive at a different problem. This is a great paper from 3 years ago from Lopez and Richtering. And this value A is the same as psi in our expression here. And you can look at these values and see that they're kind of close to each other, but there is some deviation. And the average value that's in the literature is -9. And Lopez and Richtering went back and did a careful analysis of all the data they could find and actually found that the value was closer to -2. So here's an example of those unelucidated discrepancies between thermodynamic data in the literature. So this was our opportunity to test this model. So according to this model, if psi is -2, then the cutoff distance is 60 nanometers between the concentrated and semi-dilute regions, which means the brush will be stretched along the entire contour. But if it's closer to the average value in the literature, then this should be 17 nanometers, which means the thickness of the brush is only about 10 nanometers. So we did the same thing that we did with the polymethyl acrylate. We synthesized deuterated NIPAM monomer and then polymerized it. So we have a sample with just a normal brush, and then the isotopic block copolymer, and we chose these molecular weights so that if they were fully stretched, the length of the entire brush is about 20 nanometers. And so this allows us to test whether or not one of these conditions is true. So you can see again, just by changing the isotopes in the brush, you get significantly different scattering patterns, and this gives us an opportunity to analyze these to come to some kind of result here. So we used the same models before, and I'm showing schematically what the different deuteration schemes represent. But at the end of the day, we measure these at 2 temperatures, 5 degrees and 15 degrees. And if we fit all 3 of these deuteration schemes, we have to arrive at the same result. Assuming that the deuteration doesn't impact the interaction, then all of these different deuteration conditions are looking at different pieces of the polymer chain. So we have to get a single unified picture. There are also constraints here. The polymer chain can be stretched, but it can't be stretched longer than its maximum extension, R max, which is about 20 nanometers. And what we find when we analyze it is the brush thicknesses are about 12 to 15 nanometers, and they're highly stretched. And what we mean is that by highly stretched, it looks like the end-to-end distance, or I should say more strongly, the end-to-end distance scales as the degree of polymerization to the 0.8 power. So these polymer chains are behaving as like they're entirely in the concentrated polymer brush region. So this means that that parameter psi has to be greater than -9, which is closer to what Lopez and Richtering's analysis provided, which is that it's -2. So we find that a value that's closer to the second analysis than it is to the value that's commonly reported in the literature. So to summarize the second part, we connected the Flory-Rehner analysis of microgels using DLS with the Daoud-Cotton model that was derived for star polymers and polymer grafted nanoparticles. And I'd like to highlight a couple of points here about this. The first is that when you measure homopolymer solution thermodynamics by neutron scattering, typically you prepare dilute solutions and you use the random phase approximation. You can't use the random phase approximation, as far as we know, when you have polymer grafted nanoparticles. So it's really difficult to get the thermodynamic information from polymer grafted nanoparticles. If you do DLS on microgels and use the Flory-Rehner approach to understand how they swell, then you can get an interaction parameter out of that analysis. So the point here is that if we measure the structure of polymer grafted nanoparticles, we can extract that parameter psi, and that can be used to calculate an interaction parameter. So finally, we use neutron scattering, but the approach that we took to get the thickness of the brush can also be done with DLS measurements. So in the event that you have something that you can't gel, if it's impossible to get a microgel for your particular polymer, then if you can measure the polymer grafted nanoparticle conformation, then you can get the parameters that describe its thermodynamic behavior. So the take-home message I'd like to leave you with today is that measurements of microgel swelling can yield predictions of the grafted polymer conformation, but also the measurement of grafted polymer conformation can yield the thermodynamic data. And finally, what I really enjoy about this work is that if you measure the polymer grafted nanoparticles and you measure the conformation of the chains, you can get predictions of how microgels will swell. So I'd like to leave you with an acknowledgement of the people who did this work. So they're actually sitting in the back here. Some of you may recognize Gabrielle and Luis though. So this was our group about a year ago. So they did the work. We collaborate with scientists at NIST, specifically Bulam Hamouda for structure and Antonio Ferrone for dynamics, as well as Nicole Steinmetz and John Pekorski, whom some of you may know. This work was supported by the National Science Foundation in the US, as well as the Ohio Supercomputer Center, NIST, and not this work in particular, but a company in Canada. And so finally, thank you for the invitation. I'm glad I got to talk to you. This is the first time I've got to share scientific work in many, many, many months. And thanks for paying attention. Thank you.
Thank you, Professor Michael, for this great presentation. We now open the floor to question. Anyone who has a question can just open up the microphone and speak, or maybe put it in the chat and we can read it then. Anyone on YouTube can also write the question on the YouTube chat and we will read it here. So who wants to be the first?
May I ask a very silly question? Mike, can you compare light scattering, what you can get from this, with neutron scattering? Just to make a point, what the advantage
Yes.
with neutron scattering?
Yes, absolutely. So I'm going to go back a few slides and show you something that's not neutron scattering. So this is an example, and you could take the approach that we did with neutron scattering. You could do it in your lab without a nuclear reactor. The downside is that you have to prepare many, many, many different molecular weights of polymer. So you're going to have to synthesize many different batches of polymer grafted nanoparticles. But what you can see is you can see the trends here that as you're changing the molecular weight, you can see the transition between the stretched and the unstretched regions. So if you wanted to get that transition point RC, this point right here is going to be RC. It's going to be that transition between the two regions. So if you were only doing light scattering, you could prepare all these molecular weights of the grafted particles, identify where RC is, and then from that you could calculate the thermodynamic properties. One thing that you may miss if you do light scattering is you may miss the ability to simultaneously resolve different parts of the brush. So although you're seeing trends in how the thickness of the brush is increasing, you may not be able to see, for example, that the inner region is a spherical shell and that there are globules on the outside. You may only see that from light scattering, the thickness of the shell increases, let's say linearly, and then afterwards increases as some different power, but it doesn't necessarily tell you the shape and the even distribution of these on the particles. So the neutron scattering is giving you
sorry, in order to see this local structure, you have to have some kind of model here, because it's not clear to me looking at this scattering that you have so complicated structure. Do you?
So that's a great point. And so when we originally did this experiment in particular, we noticed that we had this kind of shape here, if you see these peaks,
Yeah.
that were due to the scattering of something that was spherical. But what we also saw was this foot here. And the slope of this line told us that what is on the outside of this sphere must be a compact object. So in some sense, you know, it need not be spherical. I guess they could be triangles or something crazy, but it was telling us a bit more information just based on the slope of these things alone and where these different transitions took place. At the same time, even comparing neutrons to photons to then electrons, this reconstruction of the cryo-EM image, there, you can even see if you look at this image here, there are certain assumptions about the symmetry of the object. And so that's maybe a downside to using the electron microscope. And then I guess, go ahead.
Sorry, what means this minimum, this minimum and this maximum in the middle of the scattering?
This part here?
Yeah.
So this part here, we call this the ringing pattern. These maxima and minima have to do with the fact that the inner portion of the object is of uniform density and spherically symmetric. So in the solution of the form factors, these oscillations come from the fact that the scattering is described by a Bessel function.
Okay, interesting. So the other question is, how scattering is this scattering information? Well, because you have shown 2 or 3 measurements, it looks to me a little bit different. And the information looks to me that is very small change in slope or data may give you some very different information. So I wonder how precise, how scattering is this scattering information.
Yep, that's a great question. I'm looking on my monitor here. It's hard to see. First of all, you can see the error bars for the measurement are, if you really look, they're there. They're smaller than the points. So that's one indication for a single measurement. If I was to take several measurements, several independent measurements, we would get almost exactly the same scattering pattern. So the scattering patterns themselves are actually not scattered, if I want to use your words. But you hit on an excellent point, which is that sometimes these changes are subtle, but these subtle changes in slope out here, for example, I don't know if I have, let me blow it up so we can look at something bigger. If the slope out here on a double log plot went from -2 to -1.67, I mean, that's huge. That's the difference between a Gaussian chain and a swollen coil. So those, even though they seem subtle, you know, they're a hallmark signature of these structural changes.
Very distinct. Thank you, Mike.
Professor Raja, would you like to speak?
Yes. Thank you, Professor Michael. I have one clarification about Flory-Rehner model. I remember the free energy of mixing and free energy of elastic thing are additive in this original model of Flory-Rehner, right?
Yes.
But in dynamics, will it still be valid? Can you add them? Because there may be a lag between the effects.
Sure. Do you mean well, the dynamics of the polymer chains themselves?
Mm.
Or do you mean dynamic measurements?
Dynamics of measurement. For example, you go from dry to swollen. With time.
Well, that's
continuously adds these two, right? Elasticity and mixing.
Mm-hmm. That's a great point. I mean, the only thing that I would point out here is that, you know, as well, there's two things. As far as we know, well, I guess the basic assumption of the model is that this is equilibrium swelling. So the swelling process itself, those two terms are likely not additive, right? There's this swelling effect that I'm not talking about here. Once it is swollen, though, I think that the fact that they're additive is probably an okay approximation. But I do want to point out one major issue with using the Flory-Rehner model, and that is that here, when we combine all these terms together and we express the Flory-Huggins parameter as this function and as this function of the volume fraction of the swollen gel and the dry volume fraction of the original network, getting this value here is one of the big problems, and that's the reason that these authors claim that there's such a discrepancy between the values that they get for this parameter and the values that are given in the literature. You can see, for example, the phi 0 is the volume fraction of dry polymer. In the literature, they assume this to be, or they calculate this to be 0.8. When they redid their analysis, they said for the volume that those particles take up, the polymer is actually only 3%. So I think maybe this may be the bigger issue, at least in this application of the Flory-Rehner theory, than other ones.
The other question is actually two questions. One is how far can we use lattice model, 2D lattice models to describe such dynamics of this process? Not scattering, I'm talking just dynamics of it.
Yeah, that's a great question. I don't have a good feel for how far we can push the lattice models. I'm not sure.
Now, what I'm asking is, for example, what is the similarity between a protein unfolding and, say, your brush, grafted brush behavior polymerization? Is there some similarity between the behavior of protein unfolding? So they all these tetramer toy models, simple models.
That's a good, you know, I haven't looked at the similarities between the two. Ours are a little weird because we still don't, at least in my case, we still don't have a good picture of, I wish I could pull up a picture quickly for you here. This is the question we sought to answer when we started this study, which was, again, we grow these chains from the surface, but you have a very stretched dense region here and a more ideal region. So the question we wanted to answer is, if you have this kind of structure and it collapses because of this thermal transition, in some ways that is similar to a protein. In some sense, you're neglecting a lot of effects that are present in proteins. But we wanted to know what would happen to the structure here, because it's so crowded down here that it can only fold so much in response to the poor solvent conditions. Unfortunately, the choice of molecular weight that we had here, we don't have a good answer yet to that.
Does it expel solvent when it collapses?
That's what we were thinking. It would expel solvent and then maybe it can get closer. We didn't see that effect, and there's many reasons why we can't see that effect. We have issues with neutron scattering going to higher temperatures, because these particles aggregate to a very small extent, and that just destroys the scattering pattern. It makes it very difficult for us to analyze them. But it may be possible with DLS, and taking the approach that Fred was suggesting, DLS and, you know, many molecular weights and going to higher temperature, maybe by looking at the trends, we could start to get some idea of what's happening to the shape of the brush. But again, our system is much simpler than a protein, because proteins have all kinds of, you know, heterogeneous interactions, right?
Okay.
Yeah.
Thank you very much. Still, there is some more doubt is there. How do you know it may not be going through an intermediate structure?
Great question. That's we don't know. I mean, in terms of the conformation of the chain, the way I draw it here is really an exaggeration that it's such a sharp transition. I don't know if there's an intermediate one, but what I can tell you is that the conformation along the contour of the polymer, it should gradually go from highly stretched to relaxed. It shouldn't be the sharp transition. So certainly that's present.
Thank you very much. It's a beautiful talk.
Thank you.
Enjoyable listening to you. Thank you very much, Professor Michael.
Thanks.
Interesting.
Can I ask a question?
Go on.
Thank you. Mike, would it be interesting to congrats on the talk, by the way, it was great. Do you think it would be interesting to vary the radius of the core? Is that something that people do to make the chain that's the part of the chain that's closer to the surface or the interface between the nanoparticle and the polymer, make it less crowded and how would the polymer chain conformation change with the curvature really of the particle and the radius of the particle? Do you think that's interesting and worth looking into, or?
Well, that's a great observation, because there is one other study in the literature that looks at NIPAM that's grafted to spherical particles. They take a different approach to analyzing it, and they don't do the deuteration thing that we do. But the point there is that this parameter here obviously controls the transition between those two regions. Their particles were 100 nanometers in radius, so they're much bigger than ours. Ours are about 15 nanometers in radius.
Okay.
In their case, they find that their chains are super highly stretched. And so to answer your question, there is some use in doing that. If you can get monodisperse smaller particles, then if you do that, then you can keep the same molecular weight of your brush, but you can shift the position of the transition between the two regions. And because these things are all related, basically at the end of the day, what you want is the transition between those two brush regions, and then what this value of A2 has to be for that to be true. And so by shifting the position like that, then absolutely you can further tease out those parameters.
Okay, thank you.
Does anyone have another question? So let me just ask something. Professor Michael, I heard you and Marlon talking before the meeting about a YouTube channel that you have, and the simulation of, if I understood correctly, it's a virtual reality simulation of molecular dynamics. Is that it?
That is correct, yeah.
So can you just tell something to everybody about it?
Sure. So you can get to the channel from my either my Twitter account or from my webpage that's at the bottom here. But what I did is Microsoft released what they call the HoloLens, and it's not quite virtual reality, it's mixed reality. So it's a headset that goes on that you wear, and it's a Windows 10 computer, and it projects holograms on top of what you're already seeing. So Mercedes is going to use this in their auto shops to help fix cars. If the mechanic is unsure where the part is that they need to remove, then the HoloLens can project on the image of the engine where that part is. In our case, I wrote, I guess it's a molecular dynamics-like simulation. It's a Langevin dynamics simulation of a polymer chain in an implicit solvent. And the point was to use it for a class of mine. And yeah, it just projects a polymer chain in front of you, and you can switch between the freely jointed chain, freely rotating chain, and in real time, it's integrating the equations of motion, just like a normal MD simulation would do. So the goal was that it could help students visualize what these polymer chains look like, and also show what these models are doing for people who are simulating them. So I'm going to release it also on the iPhone and on Android for free soon. And some of the source code is already available for free. And you can also get that from my webpage if you just want to poke around and see how the model was written.
Interesting.
Okay. Thank you for that. So does anyone have a last question before we wrap it up and go? If not, so let us just thank again Professor Michael for the presentation. Thank you. It was very, very interesting.
Thank you very much. It was nice talking to everybody.